Here's one more example problem to look at. It's a production and distribution problem, and it turns out to be a linear constrained problem, and we'll take that into account when we do our solution. So here's what we've got. We've got a company that has 4 manufacturing plants across the U.S. They can each produce a certain amount of adhesive. They also have 3 customers across the U.S. and they have contracts to supply that adhesive. All the plants have different costs, and also they have different capacities, and also the customers have ordered different volumes, and so they are charged different prices based on that. And of course, one more variable here, the shipping costs. They're different for each plant and customer combination. So here are our 4 manufacturing plants: Buffalo, New York; Gary, Indiana; New Orleans, Louisiana; and Portland, Oregon. So the largest of those plants is in Gary, Indiana, which can do 22,000 gallons a week. And Portland is the smallest with a capacity of 10,000. Also, the costs are higher in Portland, and they're the lowest down in New Orleans. Our 3 customers are spread out as well in Minnesota, California, and Texas. The company in Minnesota orders the most, 26,000 gallons a week, so they pay the smallest price of $2 a pound. And in Texas they order the least, and so their cost is at $3 a pound. Now if we look at the shipping costs from New Orleans, of course the further we're going to ship it, the more it costs per gallon to ship. Gary, Indiana, similar kind of situation. If they're shipping to Minnesota, the costs are pretty low. If they're shipping to California, then they're a good bit higher. Similar for Buffalo. And finally from Portland. If Portland shipping down the coast to California, the costs are pretty low. Alright, so what that means is we have 12 independent variables, because what we can look at are how much volume are we making, how much adhesive are we making at each plant and shipped to each customer. So there's our optimization problem. Obviously what we're trying to maximize in this case is the amount of profit. So total sales cost minus the total costs, total sales minus total costs. We want to change the 12 independent variables, but we have constraints. We can't make it all in one plant because they have various capacities, and we have to fulfill the orders we have from each of the 3 customers. Okay, so this is again on that spreadsheet that I've posted, and let's take a look at it. So here, these are constants. These are the capacities and the cost to produce. These are the orders and the price per gallon, and here are the shipping costs. So all the stuff that's in blue are the constants here. These are our independent variables right here. How much do we make at each plant and ship to each customer? So over here we have some formulas that will sum up the amount made at each plant, and will sum up the amount that's shipped to each customers. These are kind of here for information. Do we have excess capacity at any of the plants? Once we figure this out, how much profit are we making by each plant, and what's our profit by customer? So again, those are for information only. Okay, let's pull up Solver. And again, what are we trying to do? We're trying to maximize profit. So we click on profit as our objective cell. We want to maximize it, and we want to do it by changing these 12 independent variables. Okay, but now I've got to add some constraints. So the first constraint is that, for example, let's go to the production in New Orleans. The total production has to be less than or equal to its capacity. And we'll do that for the other plants as well. The total production at Gary, less than or equal to its capacity. Total production at Buffalo, less than or equal to its capacity. And finally, total production at Portland, less than or equal to its capacity of 10,000 gallons. Now we also have to make sure we fill our orders. So the total sales volumes to Midwestern Manufacturing, and we'll make this equal to their order. Similarly for the West Coast, equal to its order volume. And our last one is that this Texas manufacturing sales volume is equal to its order. And click OK. So you can see there are 7 constraints, that the volume produced is less than or equal to capacities, and the amount shipped is equal to each orders. Okay, unconstrained variables non-negative, that would be okay, but now notice right here by default this is non-linear. But it's like we talked about with if everything's linear, the simplex method, it only checks the possible solutions, the corner points when we're looking at 2 variable kind of problems. So when you have linear problems like this, especially with a lot of variables, you want to pick the simplex method to do that. All right, let's click solve. Hopefully I did everything correct. It says we found a solution. And so there's our maximum profit, $67,350. And you can see the amount we've made at each plant and shipped. You also see that New Orleans and Gary are operating at their total capacity. Buffalo has some capacity left. In Portland, we actually haven't made anything in Portland because of its high costs. So there's the profit by plant and the profit by customer. So we'll kind of skip through the stuff that we just did. And again, nice thing about using Solver is you can look at variations without having to start over again. By the way, here is our solution of what gets made and shipped from each location. And again, no production at Portland because of its high costs, and New Orleans and Gary producing at full capacity. So what if, we can do a couple of different what ifs here. What if something happens in New Orleans so that part of the plant has to be shut down temporarily, and so its capacity now is only 9,000 gallons? What if the Texas increases their orders? Or what if you have a strike in Buffalo and you have to make concessions and so the production cost goes up there? Again, we can look at each of those pretty easily, and all of them are going to change what your optimal solution is. So here's the first one. If we reduce the capacity in New Orleans down to 9,000, all I have to do is change that here and run Solver again, and you can see there's our profit. You can see now that Portland, which had 0 production before, now has to pick up some of that slack. Other than that, everything's running at full capacity. If the Texas plant increased their order to 15,000 gallons, you can see the profit goes up quite a bit, although the Portland plant, again, would still be producing nothing at that point. All the other plants would be running at full capacity. And finally, the last one, if we increase the production costs in Buffalo, then suddenly it's not cost effective anymore. So you have the Portland plant taking over a lot of the slack and shipping things, especially onto the West Coast, because of that lower cost. So again, a lot of what if analysis you can do once you get this set up. So a couple things about that. We used the simplex method because of the fact that everything was linear here. Everything, again, is, we could have done this, by the way, on a couple of the other examples we looked at, but the more variables you have, the more the efficiency of the simplex method is preferred. We could have used a nonlinear solver here, and depending on what guess values you put in, you may end up with a different solution, and that would be a local max and not necessarily the absolute max like you are going to find with the simplex method. Just one other thing to wrap this whole thing up. A lot of engineering problems, you look for an optimal solution, and so learning how to use Solver will come in handy in a lot of different courses. And if you're going to be an industrial and systems engineering concentration student, you'll take a course in systems optimization. A lot of students, say in mechanical as well, like to take this as a tech elective. So again, it's a field that you can do a lot of things in, and as you can imagine, a lot of, whether it's a process or a design of a product that you're working out, you're almost always trying to find some optimum solution, and this is a good tool for being able to do that.